Okay, we can start. Now I will present for the second speakers for today's webinar. Dr. Jimmy Chandra is an assistant professor at the Civil Engineering Department of Petra University, and he is currently the head of a structural engineering laboratory. So we still have many improvements that can be used for the research in the structure connection and everything. So he received his bachelor degree from Petra University, master from AIT Thailand, and then the doctoral degree from Nanyang Technological University Singapore. His research interests include the behavior and seismic performance evaluation of reinforced concrete structures. So today he will talk about the future research or potential research for the connection of precast. And then if you, please, the time is yours, Dr. Jimmy Chandra.
Okay, thank you, Dr. Antoni, for introducing me. So may I allow share my screen?
Yes.
Okay, everybody can see my screen now?
Yes, you can use the slideshow, please. Just check it. Okay. Yes.
Okay, good afternoon, ladies and gentlemen. As being introduced by Dr. Antoni, my name is Jimmy. So today I will present my presentation with the title Precast Concrete Element Connections. So if Mr. Nishant already talked much about the application of the precast concrete element connection in industry. So in this session, I will talk more about the literature and the research in these precast concrete element connections. So before I start, let me further introduce myself. So as been introduced, I'm a lecturer at the Petra University. I'm teaching the reinforced concrete design and advanced concrete structures. And I also as a structural engineer, so mostly I design the reinforced concrete and steel buildings. So due to the precast concrete industries in Indonesia is not so popular, I have to admit that I never had a chance to design a complete precast concrete buildings. So that is my background. So the third one, as a researcher, I with my interest in the behavior and seismic performance evaluation in the reinforced concrete structure. So I will talk more about my experience, especially in the experimental testing of the reinforced concrete structures. So I have experience to test some RC beams, it's ordinary reinforced concrete beams, and high strength concrete beams with the concrete strength up more than 100 megapascal. And then I also have the experience to test the high strength steel fiber reinforced concrete beam. So we put some steel fiber to increase the shear strength of the beams. And then also have the very, very rare experience to test the strength concrete giant beam. So this is, I call the giant because this is the beam is really big. So the dimensions, the height is around 1.8 meter. So it's higher than me. And the long is, the length of the beam is 14 meter long. So 1/4. So it's twice of the foot soccer goal. So it's a 14 meter long. So it's a very rare experience to test such big beams. So rather aside of beam, I also have the experience to test high strength concrete two-way slabs. In this case, we investigate the shear capacity, the punching shear, and also the high strength steel fiber reinforced concrete two-way slabs. So we also put the steel fiber to increase the punching shear strength of the steel fiber reinforced concrete slabs. And for the pre-stressed concrete, so I ever have experience in testing the pre-stressed concrete bubble deck slab. So This bubble deck is like hollow core slab actually, but the hollow core slab is behaving in one way. The bubble deck is a two-way slab. So is we put some big balls inside of the slab and we cast so that we can save the material cost for the slabs. So this is one of the very interesting experience that I like to share with all of you. Actually, this is my first so-called training when I came to Nanyang Technological University at the time. So at the time, my late supervisor had a research project in this PC bubble deck slabs. So we test the PC bubble deck slabs to investigate the punching shear capacity. And then when we are performing the experimental testing, he asked me and my friend to climb on the top of the slab to investigate the crack and to measure the crack width during this testing. So when the slab was about to fail, he just said to me, okay, just calm, stay calm and don't jump, you will be safe. And thank God I'm still here. So it was, I and my friend, we can see the slab failing in punching shear. It's a shear is a very brittle failure. So the failure was very sudden and we can see the slab fail, making a circular cracks around us. So we are standing at the top of the column support, so we are safe. So it was a very interesting experience for me because it's the first time we test this punching shear for the bubble deck slab. And then I also have the experience to test high-strength concrete walls. This is for my doctoral degree. So we test 7 high-strength concrete walls with concrete strength more than 100 megapascal. And we also have some publications in the ACI Structural Journal for this research. So, okay, so now I will enter the presentation. So my presentation outlines is first, I will start with the introduction, and the second, I will talk a little bit about the basic dry-turn criteria and the basic fault transfer mechanism. And that one, I will explain, maybe I will skip a lot of slides because Mr. Nishant already explained more detailed about the many connections. So the fourth one will be the upcoming research that we will be doing in the Petra Christian University. So connection design is one of the most important aspects in the design of precast concrete structures. So this is because this is the main difference between the cast-in-place monolithic reinforced concrete structures and the precast. So it's essentially we design concrete structures like we are designing steel structures. So we have to design the connections. So this is one of the most important aspects. So the connections are designed to transfer loads, restrain movement, and provide stability. So this is, I think it's clear. And the connections detailing should consider allowable tolerance, provide good fit between selected materials, avoid interference between strand or reinforced steel and the connection components such as heated concrete anchors or deformed bar anchors. So this is there are many types of connection in one particular precast concrete structures. It's a floor to wall and wall to wall, column to column, column to foundation, floor to beam, and beam to column. So in the initially I want to talk about the lesson learned from past earthquake disaster. So precast concrete building, if not designed properly, can also fail. So one of the cause of the failure is the failure of the connections. Of course, there are many other cause of the failure, but here I want to highlight the connections failure. So this is an example of the connections failure due to earthquake. As we can see here, you can see that the connection from beam to the column is damaged, and that's why the building is collapsed. And second one, we can see also there is some damage in this connection, the concrete crush and some of the concrete spoil here. And then here also one of the examples of the roof system that collapsed because of the failure of the connection here. As we can see, the connection failed and thus the roof system collapsed. Okay, and then after that, we want to move to the basic design criteria. So the first one that we need to consider is the strength. So strength means transfer forces, including those caused by volume change and those required to maintain stability. So this is the load combination that I took from ACI 318 M14 chapter 5. So in the actually the ACI code now is already we have a 31819, right? So but since in Indonesia our reinforced concrete code SNI 2847 2019 is still adopting ACI 31814. So this is I took from ACI 31814. So this is the basic load combination that we need to consider to design the reinforced concrete structures and also the precast concrete structures. So we have a dead load, lift load, earthquake, and so on. And then we also have the strength reduction factors. So for moment, shear, torsion, bending, and so on. And in the right side, we also have the strength reduction factor for anchors. So usually when we design for a structural member, let's say for a beam, so we make sure that the nominal moment capacity multiplied by the strength reduction factor is still equal or larger than the ultimate moment. So for the connection, we also do the same thing. And for the connection, usually we have the overstrength factor for about 1 to 1.3 to make sure that the failure doesn't happen in the connection. So the failure will happen in the member. So I think Mr. Nishant also talked that the connection is designed but around 1.25 stronger than the column itself. So the second criteria is a ductility. So the ductility is the ability to undergo relatively large elastic deformations without substantial loss of load carrying capacity. So actually, usually to achieve the ductility, we design that the steel devices yield prior to weld failure or concrete failure. So it doesn't lose the load carrying capacity. The third one is a volume change accommodation. So in concrete, we have the creep and shrinkage. And also there are temperature change strains that can cause large stresses in connections. So it will be better if the connections also allow some movement and thus relieve these stresses. So 4 is durability. So steel elements should be covered by concrete, painted or epoxy coated or galvanized when connections are exposed to weather or used in corrosive environment. I think Mr. Nishant also has explained that the bowl is covered by the grass so that it doesn't expose to the weather. Or also another strategy is to use the stainless steel in the aggressive environments. So I will not talk about the durability in details because I think we have another session in durability in the next 2 weeks. And the 5 is the fire resistance. The connections are essential to structural stability should be protected to the same degree as required for the structural components. So we have also to provide for the fire resistance. And the 6 is the constructability. So this is the one that we need to pay attention because if we do not pay attention to the constructability, then we have a problem in the field when we want to try to install the structure. So the first one, it is always better to have the standardized connections. Means if we have 10 types of different beams, maybe we can design 1 or 2 types of connection instead of having 10 types of connections. So it will create more trouble for the contractor or the suppliers. And also we try to use the standard hardware items that available in the market, and we can also to design to avoid reinforcement and hardware congestion, and material size availability and requirements, and the tolerance of the connection material as well as the erection tolerance. This is we need to pay attention. And then accessibility handling and spatial inspection for the material and within process. So this picture shows some of the typical connection failure. So if we design the connection like in the left picture, this is we can say it's impossible to install this because we cannot put the bolt inside the hole. So we cannot design the connections like this. And the right one also we can see that it's impossible to put the beam in place because we designed something like this. So we have to pay attention to the constructability when we design the connections. And the 7 is aesthetics. This is usually the architects will pay more attention to this. And then 8 is the tolerance, so the permitted variation from a specified dimension or quantity. So the connections should be designed to allow some movement, or if there is some variation in the dimension, so that we still can install the structures. Otherwise, we may have problems later in the field. The number 9 is deformations. So deformation caused by a service load need to be considered in the design of connections. So, like example, if you can see here, when the beam are loaded, they will deflect and have some rotation here. And if we don't pay attention to this detail, it can cause cracks in the beam or in the column. And also here we can see some pictures that sometimes we design the beam to be simply supported, so we don't have the negative moment. But in the reality, there will be a little bit clamping here, so that there will be a negative moment that can cause crack in the structures. So this is also we need to pay attention when we design a connection. And then from the basic design criteria, I move to the basic force transfer mechanism. So the first one is the compression. So this is several types examples of the connection that the transfer mechanism is compression. So I will not explain one by one in detail because we don't have time for that. So here most likely the force are transferred in the compressive force here. We can use maybe a strut and tie or any other theory to calculate the forces. And the second one is tension. This is a tension. Here is the column. Actually, it's a moment. So one will be in compression, one will be in tension. So when we design the tension, there are in the ACI 318 chapter 17, there are some possibility of failure modes that we need to consider. One is the steel failure, and then the pull-out failure, and then the concrete breakout or concrete splitting, side face blowout, and bond failure. So all of this can be seen further in the chapter 17 of the ACI code. And then the third one is a shear. So this is the common connection from beam to column. So we have a bolt here, so the bolt will have shear forces, and this is wall-to-wall connection. And in the same chapter, the ACI 318 chapter 17, there are also some possible failure modes that we need to consider. Is the failure of the bolt because of the shear, or the failure of the concrete, or the concrete breakout. So all of this we need to pay attention when we design the cast concrete connections. So the fourth one is bending. So this is a typical the beam to column connection. I think Mr. Nishant already explained more in detail in the previous session. So here we also have a different type of connections, and this is the pocket connection that also Mr. Nishant already explained in the previous section. The fifth is a torsion. So when we talk about the double T slab, which is carried by this L-shaped beam. So it will create the torsional forces to the torsional moment to the beam. So here we can put some plate to help to resist the torsion. Okay, so from that we move to the type of connections. This is, I think, maybe Mr. Nishant already explained. So basically we have two types of connection. One is the equivalent monolithic system. That is, we try to emulate the cast in place. So when we design this and then we grouted, we use grouting, and then the structure will behave like the monolithic RC structures. So basically we have a strong connections of limited ductility, or we have ductile connections. Second, we have the jointed system. It's the connections of limited ductility and ductile connections. And for the jointed system, we can have also the hybrid systems. I think this last 2 weeks, the Professor Sridhar also explained about the hybrid system for the precast structure walls using the unbonded post-tension tendons, which also have the self-centering behavior and reduce damage. So this is a typical of the precast concrete buildings. So we have several types of connections. I will not explain one by one in detail. So here I will go to the behavior. So we can, as we can see here, the behavior of the connections. Okay, for the linear, I think I will not talk more because this is linear is usually like this. And then for the non-linear behavior, for the equivalent monolithic, it will behave similar to the cast-in-place monolithic reinforced concrete structures. And the four jointed systems, we have 3 types. The one that limited ductility, we will have force displacement characteristic like this. And for the hybrid, we'll have the self-centering behavior here with no residual deformation. And then for the rocking system is basically similar to the hybrid system without the energy dissipation capacity. So the equivalent model system for the example is, as we can see here, for the beam column joints. So we put the connections outside the plastic hinge region. So we make the joints like the cruciform element. So you put the connections outside the plastic hinge region, and we make this connection to be stronger than the plastic hinge region. So once the earthquake happens, the plastic hinge will occur at the ends of the beam, which is similar behavior to the cast-in-place RC structures. And also for the structural wall system, the connection is in the base of the wall. So we make this connection stronger than the plastic hinge, so that the plastic hinge will happen at the base of the wall. Okay, this is, I will just skip because this, I think Mr. Nishant already explained the beam-to-beam connections. And then this is the wall connections. And this is the beam to column connection. We can have the cast in place concrete here. I think Mr. Nishant already explained in the previous sessions. We just skip here. And this is the bonded pre-stressing tendon. And this is the jointed system with limited ductility. We have a precast wall, and then we can also have the corrugated duct, and we grout it here. And okay, I will talk more about the hybrid system. So the hybrid system is basically it's a jointed system. So we use the unbonded pre-stressing tendons here that remains elastic. And then when the earthquake happens, the joint will open and it will be stretching. This is the bonded mild steel that provides the energy dissipation. And for the walls, also, you can see in the right hand side picture, the dead load or the unbonded pre-stressing tendon will provide the recentering force, and the bonded mild steel here will provide the energy dissipation. And this is the clearer picture. So in the jointed hybrid system, We can have here the unbonded tendons inside the PVC duct, and then we'll have to prevent the crushing of the beam ends, so we can use the armor plate here, and then we'll have a bond breaker here, and then this is the grounded mild steel bar. So this is what we call the jointed hybrid systems. And the four jointed rotation system is similar to the hybrid system, except for the mild steel bar. So there is no mild steel bar here. It's only the unbonded pre-stressing in the middle. So as we can see here, for the jointed rotating system, the reinforcement is terminated here, and then only the pre-stressing tendons are going through the beams. Okay, so this is some examples of connection that I took from the PCI connections manual. So in this book, they have several examples, I think more than 20 or 30 examples of the precast element connections, starting from wall to foundation, column to foundation, column to column, beam to beam, slab to beam, and so on. And also the example calculation. So if you want to learn further how to design or calculate, you can refer to this book. So here I just show some of the pictures here. The wall, we can also use the steel plates, and this is also the same. And column to foundation connections, this is similar to the one that Mr. Nishant already explained in the previous session. And this is also the same. It used the coupler, and then this is the pocket connections, column to foundation. This is column to column. We can have another type, column to column connections, beam to column. We can also have something like this, the beam to column connections, beam to beam, and so on. So I will not go into detail. You can see further in the books. And if you are interested in more, you can read these documents. So the ACI code already released some of the documents to guide us to design the cast-in-place connections or jointed systems, and the specification for tolerance, as well as the design specification for precast concrete special moment frames, diaphragms, and shear wall. So actually, we already have these documents. If you want to study further, you can see through these documents. So now I'm coming to my main part of the session is the upcoming research that we will perform in Petra Christian University. We will be doing the research on precast concrete jointed system beam column connections. So we will do the research experimentally and analytically. So here, maybe some of you come from industries or another institutions. If you would like to have collaboration with us, and we can discuss further. So our the research background is the rocking system as introduced by Priestley and Tao and verified experimentally by Priestley and McRae. So they test two beam column connections. One is the interior beam column joints, and one is the exterior beam column joint. So here, as we can see, they have the tendon duct here going across the beam, and they put the spiral here to provide confinement for the concrete. This is for the interior beam column joint, and the right side is the exterior beam column joint. And this is the result of their experiments. So as we can see here, the force displacement relationship, we can see the self-centering behavior with a very less residual deformation on the structure. So the energy dissipation capacity here, as we can see, is provided by the concrete crushing at the beam ends. So here, as we can see, at the experiment at the drift of 2.8%, we can see the beam crush at the top and at the bottom. And then for the exterior beam column joints, we also observe the similar behavior. And here the maximum drift can go up to 4% for the exterior. So here we can see also the beam crash at the ends. So after that, Professor Mender, I think those of you who doing research in concrete must have known this name, Professor Mender and his student Chang. They proposed a damage avoid design concept. So they want to prevent the damage that happened in the rocking system here by putting the steel on steel rocking interface here. So they put the steel armor in the top and the bottom of the columns. Here they did the experiment on the precast concrete column with the post-tension tendons, and they expect that this rocking system will behave something like this in the right hand side. So here the picture of the column that they test in the laboratory. So as we can see here, the maximum drift observed is about 4%. And as we can see here, the column only suffer cracks, like some flexural cracks without any damage in the bottom of the column. So the damage is only very little here in the the column, the cracks. So as we can see here, the behavior is similar to the rocking systems, except here we didn't have the energy dissipation capacity. So this is only the rocking system, and this is the gravity load plus post-tension tendons. So after this, Professor Mander, when he was in the University of Canterbury, he continued the research with his team, Lee and Solberg here. So they extend this concept, the AT concept, for the beam column joints. So they also applied the steel-to-steel armoring at the beam-to-column interface. And this, they did the bidirectional lateral loading. So they simulate the earthquake in two directions, north-south and east-west. So this is the drawings of their specimens here. As we can see, this is the drawing in the east-west. So in the east-west direction, they test like interior beam column joints with the unbonded post-tension bar here with the diagonal fuse bolt bar. And to add the energy dissipation capacity, so they introduced the external energy dissipator. So this is, they put externally the energy dissipator instead of putting internal inside the beam. So they put this external. For the north-south component, so they cast exterior beam column joint. As we can see here, the beam is only one side. So they have the different pre-stressing profile here, and also they have the external energy dissipator here in the top and the bottom of the beam. So this is their experimental setup in the University of Canterbury. So they perform the loading in two directions, in the east-west and also in the north-south direction to simulate the earthquake. So basically, they perform the testing in several steps. So the first one, they test a structure without the energy dissipator to see the behavior of the rocking system if we did not put the energy dissipator. And then for the second phase, since the damage is very low, for the second phase of the testing, they put the energy dissipator to see the effect of the additional energy dissipation capacity introduced by the external dissipators. So the top graph is the load deflation relationship. This is, they perform first the testing in the unidirectional loading, so in the east-west as well as in the north-south. So here, as we can see, in the top, the behavior is like a rocking system with a very little energy dissipation capacity. So in the bottom, the C and D, the graph here, is a specimen with energy dissipator. So as we can see here, the system have some energy dissipation capacity as introduced by the dissipators. And later on, they also perform the bidirectional lateral loading. So here the force displacement relationship for the pre-stress only, and this is for pre-stress and the dissipator. Here we can see that when they're using the dissipator, the system have the more energy dissipation capacity. And later on, they also continued instead of quasi-static cyclic loading, they also perform the QED testing. So they try to simulate the earthquake. So here they have three types of earthquake with presence of the 90% design-based earthquake, 50% of maximum concentrated earthquake, and 90% of maximum concentrated earthquake with this respective maximum drift. So this, in the right-hand side, we can see the load displacement curve of the specimens when subjected to this earthquake. So here, as we can see, for the 90% of maximum concentrated earthquake, the specimen can have the self-centering behavior with very less residual deformation. And here is the picture of the specimens after the testing here at the 4% drift. So 4% drift is already to represent the 90% of maximum considered earthquake. So as we can see here, the damage is only very little in the beam. There are some little cracks here. And for the columns, here we can see there we can hardly see any cracks in the column. So the column looks like still healthy. So with this research, they conclude that this D80 frame structure will remain operational following a design level earthquake. And then the AD structures will not collapse and will be repairable following a very rare earthquake. This very rare earthquake, maximum concentrated earthquake, is to represent the earthquake that have the return period of 2,500 years. When we compare with our cast-in-place monolithic structures, when subjected to this MCE, our objective is usually a collapse prevention. So I will just explain in the next slides about that. The third one, the mild steel bars that are used as energy dissipators in the D80 frame structures can be replaced after an earthquake. So of course, after the earthquake, this energy dissipator will be damaged. So we can see some the dissipator buckle after the 4% drift. So we can replace after earthquake, and then we can have new structures. And then the fourth one, in this D80 frame structure, cast in place concrete at beam end helps to alleviate construction tolerance issues and ensures the face of the beam is aligned properly with the column. So this is the metric performance from VEMA 356. So I want to explain. So as compared to our, let's say, cast in place monolithic RC structures, usually our seismic design code aims for the basic safety objectives. Means for the design level earthquake, will have the life safety, and for the maximum considered earthquake, we'll have the collapse prevention. This is the maximum considered earthquake, which is with the probability of occurrence of 2% for the 50 years, is with which is equal for the earthquake with 2,500 year return period. So for this very rare earthquake, our cast in place monolithic RC structures will be severely damaged. So as long as and then they should not collapse, yeah. So but we cannot use again the structure, so we have to demolish and we have to rebuild. For this, the AD structures, they aim for the enhanced objectives. So here, as we can see, the enhanced objectives for the design level earthquake, the AD structure will have the operational performance here, I. So I is the enhanced objectives. And also for the maximum cost of the earthquake will be repairable. Repairable, actually, there is some criteria here. It's about the damage control between N and O. So N and O is also enhanced objectives. So actually, this AD structure performs better than the cast in place monolithic structures. Not only that, if we talk about the economic cost, I mean, if we talk about the economical value, so after very rare earthquake, instead of demolish and building a new structure, in the AD structure, we just repair a little bit. So we just repair the beams, the cracks, and we change the energy dissipator. That's it. We can restore the structural performance. Not only that, we can also say in terms of the business opportunities loss. So let's say if the structures is a shopping mall, so if we have a cast in place monolithic structures, the structure will be severely damaged. We need to demolish and rebuild. It will take another 1 or 2 years to rebuild. So in 2 years, you cannot use the structures. So there will be business opportunity that lost. For the DAT structures, maybe, okay, we need time to repair the structure, maybe 1 or 2 months. And then after that, we can use the structures again. So here we also talk about the business loss that if we use the cast in place monolithic RC structures. So with this concept, we are interested to investigate further in our newly developed lab. So this is the picture of Petra Christian University newly developed structural engineering lab. So here, as we can see, we have the reaction frames here with our hydraulic jack with the capacity of around 200 tons. And here is the strong wall with the capacity of 100 tons. So we already performed some testing in the RC beams. This is the pictures of our testing in the lab in our graduate course. So we test the RC beams, and also we want to test RC wall. So this is the RC wall that we make, and then we want to test in our lab with using our new equipment. And the wall here, the height is around 3.5 meter. So this we can learn many things from here. So after this, also we want to move to beam column connections. So for this research project, we also have the international collaborators. One is Dr. Hartanto Wibowo from Iowa State University. I think maybe most of you already know Dr. Hartanto, since he has been a moderator for last 2 weeks. And another one is Dr. Samir, is from Indian Institute of Technology, Jammu, India. So this is our 2 international collaborators. So maybe to introduce Dr. Samir, he will present some slides on his experience and expertise in the precast concrete structures. Maybe Dr. Samir, you can present your slides.
Yeah, can you stop your share?
Yeah, I already stopped.
Okay, stop. Okay. Hello, everyone. Very nice joining this webinar. I am Dr. Samir, working at IIT Jammu. I have worked on precast elements during my PhD, and from then, like from past almost 10 years, I am working on precast elements. I have also worked on several metro projects using precast elements, box girders, pre-tension and post-tension beams and all. So, and during my PhD, I have worked on hollow core slabs, and since then I have been evaluating various parameters with respect to the hollow core slabs and their performance. Today I will briefly talk about the effect of the openings in the hollow core slabs. So you would have already seen what is a hollow core slab. Hollow core slab are pre-stressed precast elements which have longitudinal cores in the cross section. So here you can see there are several cores along the length, and the figure in the middle, you can see the longitudinal cores, right? So they reduce the cross-sectional area, and since these are pre-stressed elements, the P by A component, by reducing the A in the denominator, and you will be increasing the pre-stressing stress, right? So that gives the benefit for increasing the capacity. And apart from that, we can also save some material and use those cores for electrical conduiting or MEP conduiting, and also the air which is there in those cores provide good insulation actually. And the picture here on the right side shows the share of hollow core slabs in US. Hollow core slabs are not very widely used in other nations like in US. In US, they are very widely used for all buildings and also for bridges as bridge deck slabs. Okay, so since these are used for buildings as floor elements, openings for MEP services are provided, and this is a very commonly encountered situations. And these openings vary from very small size to very large. And very small size is okay because they do not affect the capacity or they do not alter the behavior. But sometimes for AC conduiting or for other purposes, sometimes even for the provision of columns also, large openings are provided. And here we can see the picture, the width of the hollow core slab is restricted to typically 1200 mm. Sometimes plus minus 100 mm is also provided, but typically it is 1200 mm. And these are made only with the pre-stressing strands. There are no other reinforcement bars, either transversely or longitudinally. That comes from the casting restriction itself because of the zero slump concrete, which is used to cast these slab elements. Provision of other reinforcement becomes quite difficult. So since if it is a RC slab, provision of opening is quite well studied, and also we know how to mitigate the corner stresses. However, the corner stress concentration in hollow core slab cannot be mitigated by providing the diagonal rebar or reinforcement. So in this case, we have to go for other alternatives. And in this talk, I will be presenting basically the effect of openings, but I have also studied the effect of strengthening in restoring the capacity of these hollow core slabs with opening. Due to time constraint, I will not present those results, but the experimental setup is the same. So the shear span to depth ratio is varied from 3.5 to 7.5. Basically, the shear dominated shear span to depth ratio and the flexure dominated shear span to depth ratio. The 3.5 here you can see in the third column, right? So that one, those three specimens are shear dominated specimens, and out of those, the first one is the control specimen without any opening, and the remaining two are having one flexural opening and another shear opening. Similarly, for the higher shear span to depth ratio of 7.5. So here, in the figure at the bottom, we can see there is a central opening, that is the flexural opening of 300 mm by 600 mm. These opening sizes were taken from the industry people, where they provide the MEP. They said that this would be a typical size to provide any of the AC conduiting or any other. Suppose if it is a column, 300 mm by 600 mm is a typical column size also for normal residential building. So the opening size was chosen accordingly. And because of this opening, the samples had 6 pre-stressing strands, as you can see, without any opening. And by providing an opening, 2 of those 6 got cut. So we are reducing the pre-stressing force or effect of pre-stressing by 33% and reduction in the area by 18%. And this is the casting process. Those who did not visit any precast plant for the hollow core slabs, or those who are unaware. So it basically consists of a long bed like this, on which the precasting extruder machine just moves. There are two rails on both sides on which the extruder moves. Then the strands are laid here as shown in the second figure, the pre-stressing strands. And for our experimental work, we had placed several strain gauges on the strands to measure the pre-stressing force, the stress in the strands, and as well as the losses which occur, so that we get the exact amount of pre-stressing force left in the strands. And you can see the anchorage at the non-jacking end, and after that the strands are stressed, and we were measuring the data here, the strain data in the strands while the pre-stressing is going on. And after that, here you can see the zero slump concrete being poured here in the extruder, and the extrusion process takes place after this is filled. So this is the typical casting process of hollow core slabs. And after the slabs got cured for 28 days, the strength which we got was 42 megapascal. We have designed it for a 40 megapascal strength our mix. We got 42 MPa. And after that, we took the specimens to the laboratory, and we have tested using a 4-point experimental setup. We had got all these digital image correlation, data acquisition system, strain gauges, LVDs, all the instrumentation was put in place, and we have tested. So coming to the results, the first specimen is a shear dominated 3.5 A/D ratio control specimen. It had cracked at 129 kilonewton, around 130, and the peak load was 181 kilonewton at 20.7 mm deflection here. And here we can see the shear dominated ultimate failure at the right side bottom, the complete diagonal cracks here at the failure. And the same specimen, the first slab with the opening, it had got a flexural crack here, 300 mm by 600 mm. And because of that, the peak load has gone down to 156.4 kilonewton at 56.5 mm deflection. And here we can see the crushing of concrete at the top where the opening was provided, at the line of the opening. So in the plan, if you see here, where the cursor is shown here, at this point, the concrete got crushed, and the decrease in the load was about 14%. And with a shear opening, obviously the control slab itself got failed in shear dominated mode. So the slab with the opening also failed in shear mode. But the notable point to note is the reduction in the capacity by 44%. So the pre-stressing strands were reduced by 33%, and the cross section was reduced by 18%, but the reduction is by more than 44%. So this shows the significance of stress concentration and why we should mitigate that part. Moving on, the slabs with the higher shear span to depth ratio, the control slab without any opening had got a peak load of 100 kilonewton at 67.5 mm, and as expected, a higher A/D ratio having very large deflection at failure. Here we can see at 67.5 mm, and the failure was basically by crushing of concrete at the top fiber. And the slab with the flexural opening, again, it got reduced by 34%. The failure mode remained same, but the failure crushing of concrete shifted at the line of the opening, as you can see at the figure at the right side bottom. And the slab with the shear opening and tested at higher shear span to depth ratio, it again failed in the shear dominated mode, and the decrease in the peak load was more than 33%. Definitely it was at 36%. So this is also not in linear relationship with the decrease in the pre-stressing or the cross-sectional area. Summing up, this table shows even the decrease in the energy dissipation. So here we can see the provision of openings has reduced the energy dissipation in 3.5 shear opening one by more than 28%, and in the 7.5 A/D ratio, the energy dissipation decreased by more than 46%. So the provision of opening not only reduces the capacity, but completely alters the energy dissipation capacity. So design engineers should keep this in mind before proceeding further. So with this, I stop my presentation here. Any
Okay,
questions?
thank you, Dr. Samir, for your sharing your experience and expertise in the precast oral course labs. So I think it should be the end of my session. So for those of you in the industries or in another institution who would like to have the research collaboration with us, you can we can discuss further later. Thank you. I return back to Dr. Antoni.
Okay, thank you, Dr. Jimmy Chandra and Dr. Samir Kumar Sharma Pachala. Is a very nice presentation on what is the prospect of research in the precast concrete field, and then a very nice presentation from Dr. Samir, as it's shown that what have been done in the construction when we need some hole and then we need some access, then we can make some hole, but we also need to see the actual case of the testing on what is the reduction of the capacity and what we need to do to mitigate the influence of opening. So when we cord drill is okay, but when we make a hole, then we need to see what is the effect. And thank you for Dr. Jimmy Chandra that showing us the basic of the precast connection. Besides from the Dr. Nishant Sharma has shown what is being used in the construction, we also have the potential for the advancement. Later on, we can use other type of connection. But those kind of connection is still need to be researched, and then we still have the facility, so I think it's okay. And then many of the connection type is already not patented, right? So we can use it right away. We just need to design it. So the connection is mostly not patented. And even the press system, I think that we know that we can use it also. So I think that is a good effort from the researcher. Now, the main is what is the application in the construction industry. So if you have any question, comment, please do so, and then you can raise your hand, and then I will unmute your account. Please, anybody, you can also type your question, and I will read to the Dr. Jimmy and Dr. Sharma also. Okay, Dr. Okay, Amy, oh, you can raise your hand also. So I think the time is.
Is Dr. Pamuda raising his hand?
Dr. Pamuda, you can ask question. Okay.
Mute,
oh,
mute, still mute.
Okay.
Okay.
Dr. Jimmy, can you hear my voice?
Yes, yes.
I have one question for Dr. Jimmy regarding the experiment done by Mander in Canterbury University. He tests a beam column joint using 2 directional load, right? And from the connection, we can see that he intends the column to be stronger than the beams part and their connection system. Okay. So my question is, because in my opinion, the beam only behave structurally in their major axis. So what is the point of he did the load into directionals? Did he measure anything for the beam behavior in their minor axis? Did he measure anything in the beam's minor axis in his experiment? Did he mention anything?
So, okay, thank you for the question. So, as we can see in the pictures, in the east-west direction, they test for the interior beam column joints. So they want to investigate the performance of interior beam column joints using the systems. And for the transverse direction, they actually simulate the exterior beam column joint. The beam is only one side. So actually they want to test interior and exterior at the same time, simulating one corner of a building, the exterior.
So in other words, do you think he can get similar results by doing two separate one directional loads?
Of course, for the separate one unidirectional, they want to investigate first the behavior in the unidirectional before performing the bidirectional. So in the second phase, I think the third phase, they perform the bidirectional. So they put the loading simultaneously in the east-west and the north-south.
Okay.
Of course, it's always better we can start step by step before coming to the bidirectional, because they want to check everything works well in the unidirectional loading before going to the bidirectional.
He worried that the column may not be stronger, may not be strong enough in two directional combined loading. Okay,
yeah,
thank you.
Okay. Thank you for the question.
Okay, any more question? So let me also ask the question, like from your slides about the connection, is there any what can you say? Is there any like advantage of the connection over the other, like from the experiment, and then what is the the simplest connection that we can use? So the precast structure can be made easier. Do you have any plan for that kind of research or something?
Of course, if we say the easiest, I think is the cast in place emulation, I think, or the dry connections that we can just put the elements and just connect them, and then. But this type of connection using the unbonded tendons, we offer the something that we don't have in the ordinary structures. That what I mean is the damage avoidance design that we have here. So because if you use the cast in place emulation, so the structure will behave like the cast in place monolithic RC structures. So after a big earthquake, the structure will be severely damaged. So and you may not be able to be repair it, right? It will not collapse, of course. If you design properly, it will not collapse, but you will not be able to repair. Means the structures you have to demolish and you have to rebuild. They will cost you a lot of money, and also the economic opportunity was lost. So you need to, let's say, you need to rebuild for another 1 or 2 years. You cannot use the structures. Mean the business opportunity will be lost. But using this DAT concept, so the structure, even after the very rare earthquake, it will it will have some damage, but it will be repairable, and then we can restore the performance to the previous initial state. So that we have costs to repair, we have time to repair, maybe 1 or 2 months, but still it's still a better as compared to demolish and rebuild the structures. I think that is the main advantage that the cast in place or the emulated structures that doesn't have.
Okay, yes, I understand. But like for the DAD connection, I can see the enticement of the system, right? That you can make the system almost foolproof when there's some earthquake, and then you can use it immediately. But what is the resistance of the said system, that why it's not being used more commonly? And then from my thinking is like, oh, what happened if the tendon snap and then all the building can collapse? And what do you think about that one?
Okay, for the tendons, I think of course, if we stress too much, it can snap. But in this system, they limit it to 50% of yield, so the still essentially still in an elastic part.
Oh,
so
okay.
I think it's still far away from the rupture load, if 50% of yield. And the second, why it's still not being used commercially, it's as Professor Sridharan already said last 2 weeks, you will need some time for the industries to adopt the system because it's a new in research. So we still need to convince people, right? And then also
and the
we
code
have to,
also we need to
the
have
code,
the code.
yes. In the US, of course, they already have for the jointed hybrid that the mass device put internally inside the beam, but of course that will make the repair difficult, right? If we put inside the beams. In the system, we put outside so that the repair is easy.
Yeah. Okay, that is agreeable. If there are any other question, please, from the audience. Anybody can ask, but Jimmy also can understand Indonesian. So silakan dalam bahasa Indonesia, dalam bahasa Inggris. For our participant, please give some comments on your experience or your what do you challenges that you face. So it should be also interesting because from the industrial experience, that also driving the research need. So if you have some kind of challenges, you can share for us also. Yeah. Kalau ada siapa, silakan Pak dari industri. Kalau ada tantangan-tantangan sambungan yang mungkin perlu kita selidiki bersama juga boleh. If you have any challenges or insight or anything, please share with us. Oh, okay, there is a question from Mr. Vito Lukito to Mr. Jimmy. Does by putting the connection outside the concrete structure make the connection vulnerable toward weather temperature related problem like corrosion? What do you think?
Yeah, of course, if it put outside again, the problem is the weather. So we need to cover with something that so that it can be protected against the weather. Of course, in this external dissipator, we cannot cast the dissipator because it will behave differently. What we can do is we can cover with some tube or something so that it can be covered properly and protected against the weather.
Still, we can design the element to be covered or to be to be designed against the element. We can use it. We can use the stainless. Even it's more expensive, but it's not much, right? So I think that is also a good comment. Yeah, I think beside the connection, we will also need to think about the durability. I think that is the topic for the
next 2 weeks.
Next 2 weeks, yeah. Any more comment? Kalau Pak Henry, Pak Denny, or from our partner in the construction, silakan Bapak Ibu. Ini jamnya jam sore-sore, jadi memang jam yang
difficult time, it's a weekend.
Tapi topiknya masih menarik tentang koneksi. Ya, memang seperti yang kita lihat di sesi pertama kan sudah diaplikasikan, bisa kita desain. Pertanyaannya kan yang kayak apa yang mau kita pilih, itu juga sudah ada pilihannya. Nggak harus selalu yang wet. Yang pertama kan yang ditunjukkan yang wet saja kan. Tapi kan sebenarnya banyak pilihan yang lain dan keunggulannya kita kan karena kita mulai terlambat, bukan berarti kita harus mulai dari nol lagi. Kita nggak harus memakai yang seperti pertama kali yang dipakai kan. Dan kita bisa langsung loncat pakai yang terbaru. Jadi sama seperti kalau nggak pakai handphone yang pertama ya langsung pakai handphone terbaru kan juga tetap bisa dipakai. I think that is the take. Ya mungkin begitu Pak Jimmy. Ini sesi keduanya ini nggak terlalu banyak masalah atau terlalu banyak input, but it's still okay. We learn a lot today, and kalau ada closing lagi ya. Atau Pak Hartanto mungkin kalau mau berkomentar, Pak.
Maybe Dr. Hartanto want to say something?
Like the trend and then
our international research collaborators.
Ya, ini saya unmute dulu. Oh ya sudah, silakan Pak.
I don't know what you want me to say, but
What
what
is
you
the trend for the future
everything
connection
that you said
research?
was correct.
What is the trend for the future connection research, in the United States and everything?
So the idea is we want to control the damage, right? So in order for us to control the damage, we must allow the connection to be able to move. Now, that is why the idea of using unbonded post-tension connection is very attractive, because not only that you can try to save the connection itself, but you're also going to have less loading to the structure, right? Because if you have a more flexible structure, then you attract less loading to the structure. So both ways we're winning. So if there's any other questions, then I'll be happy to answer. But the idea is that, so you are not only dissipating the energy, but you're also attracting less of the force to the building or to the structure.
Okay, I think that is a very beautiful summary for the unbonded connection. So yeah, it's behaving like when we are designing for the structure, we either using the strength, stiffness, and then our flexibility. Now we are choosing the flexibility to reduce the force, but we still keep the strength. Okay, that is still a good ending. So everyone, you can see the presentation slide. I will share it later using the same link that we have shared previously. I will also share the link by using email, and then I will see you in the coming 2 weeks. I will be speaking about the durability also with Mr. Jerry. So I think we still have one last session, and then if you have any question, please raise it, and then we will have a good discussion. And then what is the most important thing is like the idea of this webinar is to increase our knowledge in the precast construction, so that we can have a better construction, better structures, and then also the ideal aim is to have a long-lasting economical building that is seismic resistant. So thank you, everyone. And then I think the session is over. Please share the link for the questionnaire as usual, and then we will see you again in next week. Thank you.
Okay, thank you, everyone.
Thank you, Dr. Jimmy, Dr.
Thank you,
Nishant,
Pak Jimmy.
Sharma, and then also the guest speaker, Dr. Sarim. Ya. Selamat sore, Bapak Ibu. Selamat berhari Minggu. Berhari
Pekan.
weekend. Berhari weekend.
Malam Minggu.
Malam Minggu. Sampai ketemu 2 minggu lagi terakhir. Jadi Pak Artanto sudah bergadang terus ini.
Pak Jimmy itu sudah dapat sponsor belum itu untuk tesnya itu? Ini Pak Jimmy harus cari sponsor.
Tadi, duitnya berapa banyak, Pak?
Nah, ini Pak Jimmy.
Itu.
Bisa ditodong itu Pak Jimmy yang
Iya nih, kita butuh sponsor ini dari Rieckermann ini.
Ini ada partnernya juga kan dari Wika, ini ada Pak Gambiro biasanya muncul selalu, dan juga yang lain.
Iya.
Ya, ini juga sebagian dari effort kita ya supaya tambah laris precastnya ini. Dalam arti ya, untuk riset, untuk konstruksi semuanya bisa.
Biasanya itu kan harus ditunjukkan dulu, oh ternyata bisa di Indonesia, baru mau pakai gitu kan. Kalau nggak ada yang nunjukkan, ini kan merasa, oh iya itu di luar negeri, di Indonesia mana bisa kan gitu biasanya.
Dari IAP itu kan sudah banyak, Pak. Terus kemudian dari Wika Gedung itu ya kita melihat. Ya memang kuncinya adalah bagaimana kita membuat owner itu juga merasa ini memang lebih ekonomis gitu ya. Ini memang lebih
mungkin kalau
simple.
ekonomisnya di awal sih mungkin enggak. Tadi kalau yang tadi saya katakan yang kalau kita kan sering gempa kan, kalau setelah gempa kita
itu
repairnya
juga good
gampang kan.
point to raise ya. Jadi istilahnya kan struktur yang mudah diperbaiki setelah gempa itu yang harusnya kita menjadi mindsetnya ke arah situ ya, bukan struktur tahan gempa, tapi struktur yang mudah diperbaiki setelah gempa. Kalau
damage
damage control gitu ya.
Ya betul, damage avoid, kita nggak rusak struktur kita.
Kalau kita
rusak ya
berpikir
elemen-elemen
seperti
tadi
itu,
yang mild steel itu Pak yang bisa diperbaiki.
Kalau kita berpikir seperti itu rasanya lebih masuk Pak. Jadi struktur precast ini kan kita enggak jual sebagai struktur yang sama seperti struktur biasa, melainkan struktur yang akan survive gempa ya dengan gerak-gerak dan tapi dengan cepat bisa kita pakai lagi setelah gempa. Dan ini sebenarnya jadi poin penting. Jadi kalau yang dulu-dulu itu kan mindsetnya adalah precast itu menggantikan struktur biasa dengan waktu yang cepat. Nah, kalau misalnya kita ganti mindsetnya dengan precast itu adalah struktur yang bisa dipakai dengan cepat setelah gempa, itu kan akan lain cerita.
Betul, makanya tadi kan saya highlight-nya itu main advantages-nya yang kita nggak punya dari yang lain.
Yang perlu diukur
jadi kita skip.
Yang perlu diukur ini bagaimana aplikasi dari DAD ini bisa diterapkan, mungkin tidak selalu untuk high rise ya. Soalnya kalau di Indonesia ini gempa.
Betul. Jadi yang di luar pulau, di mana pulau-pulau yang di
Lombok,
timur
Palu,
sana itu kan selalu gempa kan. Nah, kalau misalnya dengan mudah kita bisa pakai untuk rumah 2 lantai, 3 lantai saja, saya kira itu akan jadi lebih enticing, lebih atraktif ya, seperti yang Pak Artanto juga. Jadi ya mungkin dengan mindset seperti itu kita bisa bergerak ke depan.
The idea is when we're trying to use precast, right? So this is an alternative solution, right? So this is not the only solution. This is an alternative solution. Well, now if we are going to use precast, we can provide a very attractive alternative solution. So we have seen a paradigm shift right here, right? So before, when we're just designing for buildings using capacity design, our goal is only life safety. So your building can be damaged, but you are maintaining life safety. So you are allowing people to go out from the building, to get out and be safe, and the building can collapse, right? Now, with the new paradigm here, where we want to emphasize performance, we want to reduce the downtime, we want to reduce the damage, we want to reduce the extent of collapse that will happen. So with that in mind, then what we're trying to do is to create alternatives to make that happen. Now, one of the very attractive solution is the one that Dr. Jimmy just presented, is by using that unbounded post-tensioning system, right? So that's just one alternative. So what we want to do now is to promote the alternative, because right now people are stuck with the conventional design. And when they're stuck with the conventional design, they can't achieve the goals that are beyond the traditional capacity design. So they cannot achieve the performance levels that are more than just life safety. So that is what we're trying to get here. Now, as Dr. Antoni mentioned, there might be a lot of tests out there, but if we see those tests, how can we know that those tests are reliable, right? So that's why what we're trying to do at Petra Christian University in the lab is to create a test that is reliable, that can be a reference for many people to use. And that hopefully will also be able to change the code. So we are trying to make an impact here by doing the research in the lab at Petra Christian University to do that. That's the first step that we're trying to do, and that might be a big step for humanity, right, Dr. Jimmy?
That is a good point.
Right.
So we're trying to be
Give a contribution
better
to the
engineer,
science.
be a better engineer.
Yes, contribute.
Yeah, as we discussed also 2 weeks ago, yeah, that in Indonesia every company register their own system, and
Exactly.
most likely everybody only use what they have been registered, and others cannot use it. At the end, all the system actually cannot grow. Yeah.
Yes, so that's why here
yeah.
in the United States we typically don't patent the technology that is going to be useful for a lot of people. Right? In the academic world, where our goal is to enhance the design. Our goal is not to make money. So that's the beautiful thing about what we're trying to do here in the lab at Petra Christian University. So
Yeah.
that's so we're I think Dr. Jimmy is waiting for support. So
This is the point. This is the point, Jimmy. If I could introduce to the, let's say, a real estate owner who is not aiming to build high-rise but a mass residential building, 2 stories max, there comes the question from him. If I support these sponsorships, this research, can I use it as a, for my end only? This is going to be the question. While our goal is, in fact, to make it public, to be able to be used by everybody.
I think, itu pertanyaan yang bagus. I think that is a good question. But still, like, the research, the patent, and all. I think it's all based on the contract, and still the kepercayaannya, kepercayaan untuk pemakai, the trust from both sides, because that from the academic side we want to make a system that is applicable for everybody. So I think that is the vision. So, but still,
I don't think some patterns in the connection, I think it's a bit strange, because actually in the textbook there are already so many types of connection, and we can just copy one of them, right? So
so what we need is some system
I agree with the
verification.
Prof. Sritaran, to keep just for us, it's doesn't we are reducing the value of the knowledge. So if we're sharing this, actually the value of the knowledge will increase, because everybody is using our design.
The problem with patent is it's only delaying the progress, right? So after 10 years, your patent will expire. So after that 10 years, then somebody else will pick it up. So it doesn't matter. You're just delaying the progress. So that's why in research we typically don't patent things that is not too crucial, because we do not want to delay the progress. So
begitu. That is our conclusion for today. I think we have a good discussion, and then I think
discuss later, Pak Henry.
I think the point across is that now precast, we can see the precast as another solution for the earthquake resistant building, rather than just emulating. So the previous keyword is emulating the cast in situ. Now we are moving beyond the cast in situ. We have repairable structures. We have immediately occupancy structures, and then that is very exciting.
Some of the I must say, Pak Jimmy, some of the attendees here are closely watching. They come from a precast, but they are also in real estate.
Yeah, we can always have a collaboration in the research, or if you want to test some of your products in our lab, we also open for that.
Verification.
Let me try to find the correct party for you, for the partner. I mean, those who is not always business oriented.
Ya, nggak apa-apa. Terima kasih Bapak Ibu. Ini adalah good
Then have a
discussion.
nice day to you.
We
Bye-bye.
still have another session next 2 weeks. So I hope everybody still excited for that. Jadi ini sudah bilang. Kita akan tutup sesi ini ya Pak ya. Terima kasih Bapak Ibu.
Oke, terima
Sampai
kasih
berjumpa lagi
semuanya.
minggu depan. Saya akan
Terima kasih
close.
semua, Pak.